Identify and apply security controls in software development ecosystems. Welcome to this lesson on identifying and applying security controls in software development ecosystems. A secure software development ecosystem includes programming languages, tool sets, application security testing, and continuous integration pipelines. Without proper security controls, software may contain vulnerabilities that cybercriminals can exploit. In this lesson, we will explore security best practices for programming languages, code repositories, testing tools, and secure development environments. Let's get started. Security controls ensure that applications are developed, tested, and deployed with security in mind. Without security controls, software may be vulnerable to attacks such as SQL injection, cross-site scripting, XSS, and remote code execution. Think of security controls like seatbelts and airbags in a car. While a car may function without them, safety features protect passengers in case of an accident. Similarly, security controls protect software from cyber threats. For example, if an application does not validate user input properly, an attacker can inject malicious SQL commands to access the database and steal sensitive data. Implement security controls at every stage of development to prevent vulnerabilities. Use secure coding practices to mitigate common threats. Perform security testing regularly to detect weaknesses early. The choice of programming language and third-party libraries can significantly impact software security. First, memory-safe languages such as Python and Java prevent buffer overflows and memory corruption issues. Second, compiled languages such as C and C++ require extra security measures to prevent exploits like stack smashing. Third, using vetted libraries and frameworks reduces the risk of introducing insecure dependencies into applications. For example, a developer using an outdated JavaScript library may unknowingly introduce vulnerabilities that attackers can exploit. Use memory-safe languages whenever possible. Update third-party libraries to patch known security vulnerabilities. Avoid using unverified open-source code in critical applications. An integrated development environment (IDE) is where developers write and test code, but if not secured properly, it can become a target for cyber attacks. First, developers should enable security plugins in IDEs to scan for common vulnerabilities as they code. Second, access controls should be applied to prevent unauthorized users from modifying source code. Third, logging and monitoring should be implemented to detect suspicious activities in the development environment. For example, an insider threat could introduce backdoors into an application if developer access is not properly controlled. Use security plugins in IDEs to detect vulnerabilities in real time. Restrict developer access to critical parts of the codebase. Log and monitor development activities to detect unauthorized changes. Code repositories store software source code, making them a critical part of the software development ecosystem. If improperly managed, they can be an entry point for attackers. First, access controls should be applied to ensure that only authorify or access code repositories. Second, automated security scans should be conducted to detect secrets such as API keys or passwords accidentally stored in code. Third, version control and rollback mechanisms help prevent unauthorized code changes from being pushed into production. For example, if a developer accidentally commits an AWS secret key to a public GitHub repository, attackers can use it to gain unauthorized access to cloud resources. Use access controls to protect code repositories. Run automated scans to detect hard-coded secrets. Use version control and rollback features to prevent unauthorized changes. Application security testing ensures that software vulnerabilities are detected before deployment. First, static application security test analyzes source code for vulnerabilities before the application is run. Second, dynamic application security testing tests running applications for security flaws in real-world conditions. Third, interactive application security testing combines elements of SAST and DAST to detect security vulnerabilities at runtime. For example, a DAST scan may detect a SQL injection vulnerability in a web application that wasn't visible in the source code. Use SAST to detect vulnerabilities early in development. Perform DAST to test applications in real-world scenarios. Implement IAST to get a hybrid approach to security testing. CI/CD pipelines automate software deployment, but if not secured properly, they can be exploited to introduce malicious code into applications. First, implement automated security testing in CI/CD pipelines to detect vulnerabilities before deployment. Second, require code reviews and approval processes before merging changes into production. Third, use signed artifacts and dependency scanning to prevent the introduction of malicious software components. For example, if an attacker compromises an insecure CI/CD pipeline, they could inject backdoors into an application before it's deployed to users. Integrate security testing into CI/CD workflows. Enforce code reviews to prevent unauthorized changes. Use artifact signing and dependency scanning to verify software integrity. Many modern applications rely on open-source components, but without proper oversight, these components can introduce vulnerabilities. First, organizations use software composition analysis (SCA) tools to identify and track open-source libraries used in applications. Second, dependency scanning ensures that outdated or vulnerable third-party components are not included in production software. Third, organizations establish security policies for vetting and updating open-source software before integrating it into their applications. For example, a developer using an outdated open-source encryption library may unknowingly introduce security weaknesses into their application. Use SCA tools to track and monitor open-source dependencies. Regularly update third-party libraries to fix security vulnerabilities. Establish policies for evaluating and approving open-source components. Now, let's summarize what we've learned about identifying and applying security controls in software development ecosystems. Secure programming languages and vetted libraries reduce software vulnerabilities. Integrated development environments, IDEs, should be hardened to prevent unauthorized access. Code repositories require strict access controls and versioning to protect software integrity. Application security testing, SAST to IAST, detects vulnerabilities before deployment. CI/CD pipelines must include automated security testing and code validation. Software composition analysis, CA, helps secure open-source dependencies. By implementing these best practices, organizations can reduce software security risks and build more secure applications. This concludes our module on identifying and applying security controls in software development ecosystems. Up next, assessing the effectiveness of software security. Stay secure.